Good morning. This is Sripati Ram Prasad, Assistant Professor, Department of Mechanical Engineering, Vignan Institute of Technology and Science, Deshmukhi, Pochampalli Mandal, Nalgonda District, Andhra Pradesh. Today, I would like to give a lecture on the topic thin cylinders. Thin cylinder is a topic comes under Unit 7 in the subject Mechanics of Solids. Mechanics of Solids is one of the subject for BTech second year Mechanical Engineering. Under this topic, I will discuss what is a cylinder, what is a thin cylinder, and what is a thick cylinder, and what are the forces that are developed in a thin cylinder when it is subjected to the internal fluid pressure, and what are the various stresses that are developed in a thin cylinder, and how to design a thin cylinder. What are the various kinds of failure in a thin cylinder? We also discuss about what is meant by a circumferential strain and what is meant by a longitudinal strain and what is a volumetric strain, what is the change in the length, what is a principal stress, and how to design a thin cylinder. So under this heading, we will discuss all these things and we will do the pre-design of a thin cylinder. Here, in the subject Mechanics of Solids, the topic is thin cylinders. Depending upon the ratio between the diameter of the cylinder and the thickness of the cylinder, we can categorize the cylinders into two types. One is thin cylinder and one is thick cylinder. Suppose that if D is the diameter of the cylinder and T is the thickness of the cylinder, if the ratio between diameter and thickness is greater than 20, that is comes under thin cylinder. If diameter of the cylinder, if the ratio between the diameter of the cylinder and thickness of the cylinder is less than 20, it is a thick cylinder. Suppose that there is a cylinder, it is having a dia of 200 mm and it is having a thickness of 5 mm. So what is the ratio of D by T? 200 by 5. 200 by 5 means it comes under, what is the ratio? 200 by 5. If D is equal to 200 and T is equal to 5 mm, then what is the D by T ratio? D by T is equal to 200 by 5. This is equal to 40. So here the D by T ratio is greater than 20. So the cylinder with these dimensions of having dia 200 mm and thickness 5 mm comes under thin cylinder. Suppose that there is a cylinder having dia 50 mm and thickness 5 mm. So what is the D by T ratio? 50 by 5. It is equal to 10. Here D by T is not greater than 20. So this cylinder having a dimensions of 50 mm and 5 mm comes under the category thick cylinders. So by knowing the ratio between the diameter of the cylinder and the thickness of the cylinder, we can categorize it is whether it comes under the thin cylinder or whether it comes under a thick cylinder. Okay. So in the present topic, we discuss about the introduction and the various stresses in a cylinder and the various kinds of failures and what is principal stress, what is the diametric, what is the circumferential strain, what is the longitudinal strain, and what is the volumetric strain. If you see, you suppose that this is a cylinder. This is the length of the cylinder and this is the diameter of the cylinder. If you see from there, the front view of the cylinder will appear like this. This is the front view of the cylinder and this is the side view of a cylinder. And this is the physical cylinder, how it appears. Okay. Generally we know the applications of a cylinder. The cylinders are used generally for the transportation of fluids. So the pressure vessels or the diesel drums or some kind of water pipes or gas cylinders comes under the category of this thin cylinder. Generally the application of this thin cylinder is, it is used for the storage of fluid under pressure. So when a fluid is stored under pressure in a thin cylinder, so this is the representation of the pressure. P is the pressure that is acting in the cylinder. So when the cylinder is subjected to the internal pressure, some stresses are induced in the thin cylinders. So we will try to determine what are the various types of stresses that are induced in a thin cylinder and how to design a thin cylinder. Now let us understand what are the various stresses that are induced in a thin cylinder when subjected to the internal pressure. To understand the various stresses in a thin cylinder, first of all, we have to understand what are the various types of failure that occur in a thin cylinder when subjected to the internal fluid pressure. You suppose that this is a thin cylinder having internal pressure of P Newton per mm square with a internal dia of d mm and a thickness of t mm. When this thin cylinder is subjected to internal pressure, there are two chances of failure. The first one is known as circumferential failure and the second one is known as longitudinal failure. Let us see what is a circumferential failure. In a circumferential failure, the complete circumference of the thin cylinder will be split into two circumferences. Here you see this is the three-dimensional view of a thin cylinder. When it is subjected to the internal fluid pressure, there may be a chance the cylinder will be subjected to failure of this kind. Here what is happening? This entire circle is splitting into two halves, two troughs. Here you see this is a thin cylinder. Suppose that it is having certain ends and certain fluid is passing inside the thin cylinder. So when it is subjected to the internal fluid pressure, the cylinder may fail like this. This is the cylinder. When it is subjected to the internal fluid pressure, the chances of failure, one of the chances of failure is like this. So one half will go upside and the other half remains at the bottom. So this is what is known as the circumferential failure, because the circumference is splitting. One complete circle is becoming into two semicircles. This is what is known as a circumferential failure. And because of this circumferential failure, the stress that is induced in a thin cylinder is known as circumferential stress, or it is also known as the hoop stress. And the second kind of the failure is known as longitudinal failure. In the longitudinal failure, the entire cylinder, suppose that this is a cylinder in the beginning when the fluid enters into the cylinder, and when the fluid, because of the fluid pressure, the cylinder may be subjected to a longitudinal failure and the complete cylinder will become like this. So along the length directions, along the axis direction, the cylinder will become into two number of small cylinders. So here the single length will become into two lengths. So this is what is the failure along the longitudinal direction. So that is why this kind of the failure comes under the category longitudinal failure. So the stresses that are induced in a thin cylinder because of the longitudinal failure is known as longitudinal stress. So the conclusion is that when a cylinder is subjected to the internal fluid pressure, there are two chances of failure in a thin cylinder, and the first one is the circumferential failure and the second one is the longitudinal failure. Due to the circumferential failure, the circumferential stress is induced. This is also known as the hoop stress, and during the longitudinal failure, longitudinal stress is induced in a cylinder. Let us try to derive what is the magnitude of this circumferential stress when a cylinder of diameter d, thickness t, subjected to an internal fluid pressure of P. Okay. Now let us understand what is the magnitude of circumferential stress in a thin cylinder when subjected to the internal pressure. Here you see that when cylinder is subjected to, this is the way of circumferential failure in a thin cylinder. This is the pressure P and it is the having a diameter of d and thickness t, and this is the top view. So let's say this is the front view and this is the top view. During the circumferential failure, what happens is this particular circumference will become into two halves. You consider only half of the section. This is half of the cylinder or one trough. So what is the load that is acting on this cylinder? Suppose this is the pressure P that is acting inside the cylinder, what is represented here. So because of the action of the internal pressure, the load that is coming or the separating force or the bursting force that is acting on the cylinder is this pressure multiplied by this particular area. This area represents the projection area of the semicircle. So when the semicircle is projected, generally the area on which the pressure is acting is this is D and L. So D into L is the projected area on which the pressure is acting. So when pressure is multiplied by this projecting area, this is what is the load that is acting on the thin cylinder, or this is what is the bursting force that is separating a thin cylinder into two halves like this. So the bursting force that is separating these two thin cylinders is the pressure multiplied by this particular area. So we can write like that, the bursting force or the load, the bursting force is equal to the pressure multiplied by the projected area. What is this area? D into L, where D is the diameter and L is the length. So this is the bursting force that is separating the thin cylinder into two halves. Okay. So to resist this bursting force or to carry this load, what is the resistance force that is developed in a thin cylinders? Here you observe that during the failure generally, so what area is subjected to the failure particularly? This is the one of the area that is subjected to the failure, as well as this is one of the area that is subjected to the failure. So to carry this particular load, generally the resistance force is developed along this area as well as along this area. So the stress, that is the circumferential stress, also induced in the thin cylinder. So let us suppose FC is the circumferential stress that is induced in the thin cylinder, circumferential stress, or sometimes also referred as FH. FH is equal to hoop stress. So hoop stress or circumferential stress, both are same. So the hoop stress is induced in this particular cross section. So when this stress is multiplied by the resisting area, that will give you the resisting force to carry this bursting force, so that the cylinder may not be subjected to the circumferential failure. So if this circumferential stress is multiplied by the resisting area, it will give you the resistance offered by the cylinder. This is the load on the cylinder, what is P into DL, and this particular FC multiplied by the resisting area will give you the resistance induced in the cylinder. So here the resisting area is this area plus this area. So this area is T into L and this area is T into L. So FC is multiplied by T into L plus T into L. So FC is into 2 into T into L. So here we have seen that P into DL is the bursting force that is acting on the cylinder, so that it will be subjected to the circumferential failure. To avoid the circumferential failure, the resistance or the resisting force developed within the thin cylinder is FC multiplied by 2TL. So if you equate the bursting force with the resistance suffered by the thin cylinder along its walls, that will give you what is the magnitude of the circumferential stress. So now let us equate the two expressions. So the bursting force is equal to the resistance offered by the resisting force. So bursting force is P into DL, P into D into L, and resisting force is Fc circumferential stress multiplied by 2 into T into L. So from this, what is circumferential stress? P into D into L by 2 into T into L. It will give you P into D by 2 into T. So this expression, that is P into D by 2 into T, will give you the magnitude of the circumferential stress. It is also known as the magnitude of the hoop stress that is induced in a thin cylinder when subjected to the internal fluid pressure of magnitude P Newton per mm square. So you can also tally the units. Fc is in Newton per mm square, that is equal to pressure in Newton per mm square, and diameter is in mm, and this thickness is in mm. So it will give you Newton per mm square is equal to Newton per mm square. This is what is the circumferential stress or the hoop stress that is induced in a thin cylinder. So we have just derived this just by equating the bursting force acting on the two walls and the resisting force offered by the two walls. Now let us understand what is the magnitude of the longitudinal stress when a thin cylinder is subjected to the internal fluid pressure. Now let us understand what is the magnitude of longitudinal stress. Earlier we have seen what is a longitudinal failure. Suppose that this is a thin cylinder subjected to the internal fluid pressure. When this thin cylinder is subjected to internal fluid pressure, the chances of failure may be a single cylinder will be split into two small cylinders along its length. This is what is known as a longitudinal failure. In the beginning, the cylinder will be like this with no breakage. But once the internal fluid pressure, once the fluid is entered with internal pressure, the cylinder will become like this. This is what is known as the longitudinal failures. Now let us understand what is the longitudinal stress. So that longitudinal failure is represented here in the two dimensions. So this is a small cylinder and this is the second part of the cylinders. So during the longitudinal failure, this cylinder will move like this and the remaining half will move in the left directions. Then what is the bursting force that is separating a single cylinder into two small cylinders? If you see the side view of this, so the fluid that is here is trying to burst or trying to separate this part into some other direction. So suppose this is the fluid pressure that is existing. The pressure is acting on this particular area. When the cylinder is moving in this direction means the internal fluid that is with certain pressure is inducing some force over this particular area. So when pressure is multiplied with this particular cross-sectional area, that will give you the separating force or the bursting force that is separating the two cylinders. So if you multiply the pressure with this cross-sectional area, so if d is the diameter of the cylinder, this pi d square by 4 will give you this cross-sectional area. So when P is multiplied with pi d square by 4, that will give you the bursting force or separating force or the load on the cylinder for the cause of longitudinal failures. Okay. So to carry this particular load, the resistance force is developed in the thin cylinders. So generally, if you observe what is the resisting area during the longitudinal failure, which part of the cylinder is subject to the failure? Only this walls part. So whatever the resistance develops in the thin cylinder is only at this particular area. So this is the area where the longitudinal stress is induced. When the longitudinal stress is multiplied with this particular area, suppose d is the diameter of the cylinder, as thickness is very, very small, I can make this d as the mean diameter of this particular portion. So what is this resisting area? Pi into d, that is the perimeter, multiplied by thickness. Pi into d into t will give you the resisting area. And when this resisting area is multiplied with the longitudinal stress, that will give you the resistance or the resisting force offered by the thin cylinder to avoid longitudinal failure. So basically this expression will give you the bursting force which makes the cylinder to separate along the longitudinal direction. And this particular expression will give you the resisting force which will stop the longitudinal failures. So if you equate this bursting force with the resisting force, that's P into pi d square by 4 is equal to Fl into pi dt. This is Fl is equal to P into d by 4 into t. This will give you the magnitude of the longitudinal stress that is developed in a thin cylinders. So totally we have seen what is the magnitude of the hoop stress and what is the magnitude of the longitudinal stress. So the expression is Pd by 2t for hoop stress, and for the longitudinal stress Fl is equal to Pd by 4t. Now let us understand what is circumferential strain and what is longitudinal strain. Generally, if you observe, during the circumferential failure, the single cylinder will become into two troughs. During the circumferential failure, in general, what happens is the circumference of the cylinder will be increased and the length of the cylinder will be decreased. The circumference of the cylinder will be increased means the diameter of the cylinder will be increased and the length of the cylinder will be decreased. This is what happens when the cylinder is subjected to the circumferential stress. During the longitudinal failure, the length of the cylinder will be increased and the diameter of the cylinder will be decreased. So generally, we are interested what is the increase in the diameter of the cylinder and what is the increase in the length of the cylinder when the cylinder is subjected to the internal fluid pressures. Let us try to understand how to get the derivations for the change in dia of the cylinder, for the change in length of the cylinders. You see here, this is what is the representation of the two stresses on a cylinders. Earlier we have derived the hoop stress, or also known as the circumferential stress, that is equal to Pd by 2t. And similarly, the longitudinal stress is equal to Pd by 4t. If you represent these two stresses on a three-dimensional view of a cylinder, generally the direction of the hoop stress is along the circumference. This direction will go like this, along the circumference. So circumference will be increased and there will be a failure. That is what is the circumferential stress. And this, known as the longitudinal stress, this will be parallel to the length and this direction is longitudinal. This will make the cylinder to split into two parts along the length. So this is what is the longitudinal stress. So during the circumferential failure, sigma c will increase the dia, and during the longitudinal failure, sigma L will increase the length of the cylinder. Okay. Now this stress, this is known as the hoop stress, is also known as the major principal stress. Generally, principal stress is the maximum normal stress on a plane on which the shear stress is 0. Here in the thin cylinders, this hoop stress, or also known as the circumferential stress, is treated as the major principal stress on the thin cylinder. So that is referred by the letter sigma 1. And the sigma L, that is the longitudinal stress, is referred as minimum or minor principal stress. So this is referred by the letter sigma 2. So sigma 1 is the major principal stress, that is equal to sigma h equal to sigma c is equal to Pd by 2t. And sigma 2 is the minor principal stress, that is equal to Pd by 4t. Okay. Now let us try to understand the circumferential strain. From the basic definition, the definition for the strain is deformation per unit length, or strain is equal to the change in the length by original length. As it is circumferential strain, the definition for the circumferential strain is the change in the circumference divided by the original circumference. So, how to get the change in the circumference? We know that the circumference will be increased. So, the final circumference minus initial circumference divided by the initial circumference. Or you can also write the final circumference minus original circumference divided by original circumference. Now, let us understand the term circumferential strain. We try to understand what is the increase in the diameter of a cylinder when it is subjected to the internal fluid pressure. The expression for the circumferential strain is the change in the circumference to the original circumference. Let us suppose that there is a cylinder having the original diameter of di, and when it is subjected to the internal fluid pressure, you suppose that delta d is the increase in the diameter of the cylinder, and you suppose that df is the final diameter of the cylinder. Here you see the initial or original circumference is equal to pi into di, where di is the initial diameter of the cylinder. Final circumference is equal to pi into d naught, where d naught is the final dia. D naught is equal to df, both are same. It is the final dia, df. So I can write down this final diameter is equal to initial diameter plus the change in the diameter. Okay. Now circumferential strain is equal to final circumference minus initial circumference divided by initial circumference. So here from this expression, pi into di plus pi d minus pi into di divided by pi into di. So this pi into di will be cancelled, and the remaining term is pi into delta d by pi into di. This will give you delta d by di. So di is equal to diameters. So the circumferential strain generally referred by the letter epsilon c is equal to epsilon h is equal to delta d by d. Now let us understand what is longitudinal strain and what is volumetric strain. Suppose that there is a cylinder having dia d and length L. When the cylinder is subjected to the internal fluid pressure, the diameter will be increased as well as the length also will be increased. So what is the increase in the dia that we have seen in the circumferential strain? Circumferential strain is equal to delta d by d. Similarly, here longitudinal strain, it is represented by the letter epsilon L or EL is equal to the change in the length of the cylinder divided by the original length of the cylinder. Let us suppose L0, the original length of the cylinder, LF, the final length of the cylinder, delta L, the increase in the length of the cylinder. Epsilon L is equal to the longitudinal strain, that is equal to the final length minus initial length divided by initial length. So final length minus initial length is equal to the change in the length, that is divided by original length or the initial length. So this delta L by L will give you the longitudinal strain that is developed in a thin cylinder. Similarly, we discuss the volumetric strain. In the volumetric strain, initially generally the original dia is d and original length is L. But when the cylinder is subjected to the internal fluid pressure, this d will become d plus delta d and L will become L plus delta L. So the final volume of the cylinder will be more than the initial volume. So there is a change in the volume of the cylinder. So this change in the volume of the cylinder can be expressed by means of volumetric strain. So the definition of the volumetric strain is volumetric strain epsilon V is equal to the change in the volume divided by the original volume. You suppose that delta V is the change in the volume of the cylinder and Vi is the initial volume of the cylinder. Suppose that the cylinder having dia D and L is the length of the cylinder. So then suppose this is the dia D and this is the length L. Then this volume is equal to its cross sectional area multiplied by length. So pi d square by 4 is the cross sectional area, that is multiplied by the length. That will give you the initial volume of the cylinder. Okay. When this D becomes D plus delta D and L becomes L plus delta L, then the final volume of the cylinder is equal to pi by 4 into D plus delta D whole square into L plus delta L. So by knowing the final volume of the cylinder and by knowing the original volume of the cylinder, we can calculate the volumetric strain of a cylinder in terms of D and L. Now let us derive the expression for volumetric strain of a thin cylinder. Let us suppose that there is a thin cylinder. The initial diameter of the cylinder is D and the initial length of the cylinder is L, and the cylinder is subjected to an internal pressure of P Newton per mm square. When this thin cylinder is subjected to internal pressure, generally the length of the cylinder will be increased and the diameter of the cylinder will be increased. We suppose that delta D is the increase in the diameter of the cylinder and delta L is the increase in the length of the cylinder. So the final diameter of the cylinder will equal to D plus delta D and the final length of the cylinder will be equal to L plus delta L. So from the expression from the volumetric strain, the expression for volumetric strain is equal to the change in the volume to the original volume. But what is the change in the volume? Change in the volume is equal to the final volume minus the initial volume. So the expression change in volume by original volume is equal to the final volume minus the initial volume divided by the initial volume. Here what is the expression for the final volume? Pi by 4 into final dia whole square into final length. So pi by 4, this is the final dia, D plus delta D is the final dia whole square and this is the final length L plus delta L minus, and this is the initial volume pi by 4 into this is the initial dia and this is the initial length. Okay. Delta V by V, that is volumetric strain, is equal to pi by 4, and if you open the brackets, D plus delta D whole square, it comes as D square plus 2 into D into delta D plus delta D whole square multiplied by L plus delta L, L plus delta L minus pi by 4 into D square L divided by pi by 4 into D square L. Okay. Now here delta V by V is equal to pi by 4 into, you multiply this D square with L. So D square into L. Next D square into delta L plus 2D delta D into 2D delta D into L plus 2D delta D into delta L plus delta D square into L plus delta D square into delta L minus. So this pi by 4 is taken common here. So the remaining term is D square into L. Okay. This is what is the expression in the numerator. Then the denominator is same, pi by 4 into D square L. Next, the change in the volume to the original volume is equal to D square L plus D square into delta L plus 2 into D into delta DL minus, here we are neglecting the small differential terms. Why? Because delta D is very small, 0.003 like that, and delta L also very small. When these small differential elements are multiplied, that is again become a small number, so that we are neglecting this particular term. Okay, similarly here also delta d square, we are neglecting this term also. Here also we are neglecting this term. So what is next? What is the term? After 2d delta dl, the term is d square l divided by, this is pi by 4 is cancelled in the numerator and denominator. This is d square l. Next expression is, this is d square l plus and this is d square l minus. These two terms are cancelled. So what are the remaining terms? D square into delta l plus 2d into delta d into l, 2d into delta d into l divided by d square l. Now delta v by v is equal to, this is volumetric strain is equal to, this is d square delta l by d square l. So d square is cancelled, delta l by l is remain, delta l by l plus, this is 2 into d into delta dl by d square l, that is equal to 2 into delta d by d. But we know that delta l by l is the longitudinal strain, that is epsilon l, plus 2 into, what is delta d by d? The circumferential strain or hoop strain. So the volumetric strain is equal to the longitudinal strain, that is delta l by l, plus 2 into the circumferential strain, that is delta d by d. If you observe the cylinder dimensions, generally the three dimensions of the cylinder along its x-axis, y-axis and z-axis. Suppose that this is a cylinder, the dimension along the x-axis d, the dimension along the y-axis d, and the dimension along the z-axis l. The volumetric strain is equal to, from the basic formula, volumetric strain of a body is equal to the strain in the x direction, that is the strain in the diameter direction, that is delta d by d, plus the strain in the y direction, again delta d by d, and the strain in the z direction, delta l by l. So from the basic dimension also, by knowing the three dimensions of a cylinder, the volumetric strain is equal to delta d by d plus delta d by d plus delta l by l. We can also write down volumetric strain is equal to 2 into delta d by d plus delta l by l. That is volumetric strain is equal to longitudinal strain plus 2 into circumferential strain. But it is very easy to remember, the volumetric strain of a cylinder is equal to delta d by d plus delta d by d plus delta l by l. It is equal to 2 into delta d by d plus delta l by l. That is equal to, volumetric strain is equal to 2 into circumferential strain, 2 into epsilon c plus longitudinal strain, that is epsilon l. So delta v by v is equal to 2 into epsilon c plus epsilon l. We have expressed the volumetric strain in terms of circumferential strain and longitudinal strain. We have also expressed the volumetric strain in terms of delta d and in terms of delta l. We have seen that epsilon v is equal to 2 into epsilon c plus epsilon l. And we have also seen that epsilon v is equal to 2 into delta d by d plus delta l by l. Now let us express this volumetric strain and the hoop strain and the longitudinal strain in terms of pressure, diameter, thickness and modulus of elasticity of the cylinder material. That is epsilon v is equal to 2 into epsilon c plus epsilon l, where epsilon c is equal to circumferential strain delta d by d and epsilon l is equal to longitudinal strain delta l by l. Now let us try to express these strains in terms of P, D, T and E. Okay. If you observe the cylinder, a thin cylinder with internal fluid pressure, at any point on the circumference of the cylinder or at any point on the inner face or mid surface or outer surface, each point is subjected to two kinds of stresses. One is the hoop stress and the second one is the longitudinal stress. Here you can see this is a point on the surface of the cylinder. At this particular point, there are two stresses. One is the hoop stress or circumferential stress in the direction of the circumference, and the second one is the longitudinal stress. This is along the length of the cylinder. Okay. Now let us represent the circumferential strain in terms of circumferential stress and the longitudinal stress. Generally, this circumferential stress will try to increase the diameter of the cylinder, whereas the longitudinal stress will try to reduce the will try to increase the length. Suppose that sigma c will help to increase delta d and sigma L will reduce the delta d. Okay. So from the basic strain equations, suppose there is a point and two stresses are acting. Along x direction one stress and along y direction one stress. Suppose sigma 1 along the x direction and sigma 2 along the y direction. Both are tensile in nature. Then the strain in the x direction is equal to sigma 1 by E minus mu into sigma 2 by E. Similarly, the strain in the circumferential direction is equal to circumferential stress divided by modulus of velocity. Suppose if there is no longitudinal stress here, then what is the circumferential strain? Circumferential strain is equal to circumferential stress by modulus of velocity from the Hooke's law. But there is also a longitudinal stress. So then circumferential strain will become circumferential stress by modulus of elasticity minus mu, where mu is the Poisson's ratio of the material, multiplied by longitudinal stress by E. But what is circumferential stress? PD by 2T multiplied by E minus mu into what is longitudinal stress? PD by 4T into E. So this is what is the representation of the circumferential strain in terms of pressure, diameter, thickness and the modulus of elasticity. Similarly, the longitudinal strain is equal to, or the strain along the length direction is equal to longitudinal stress divided by E minus mu into circumferential stress divided by E. So what is longitudinal stress? PD by 4T into E minus mu into what is circumferential stress? PD by 2T into E. So from this circumferential stress is equal to, we can write down like this. You take PD by 2TE as a common term in both the terms, and this becomes 1 minus mu by 2. So PD by 2TE 1 minus mu by 2. And similarly, the longitudinal stress is equal to PD by 4TE minus mu into PD by 2TE. This is equal to, you take the common PD by 2TE. So here what is the remaining term? 1 by 2 minus mu. 1 by 2 minus mu will be the expression for the longitudinal strain in terms of this. Okay. So we already learned that volumetric strain is equal to 2 into circumferential strain plus longitudinal strain. So you just substitute the expression for the circumferential strain, that is this term here, and you substitute the expression for the longitudinal strain, that is this term here. You will get the volumetric strain in terms of P, D, T and E.